Right, so now that we're done with chapters 7 and 11, there's just a few more sort of random topics that we need to talk about. In particular, today we're going to talk about the only section from chapter 8 that we're going to cover, which is called arc length. And the idea is, if you have 2 points, and you have some kind of curve that goes between those 2 points, how long is that curve? Well, if it's a line segment, then it's just the distance between the 2 points, so that's fine. If it's a circle, then in high school geometry you learned about how to find the arc length of a circle based on a central angle. But what if it's some more obtuse shape? Perhaps something that's just defined by some random function. Say something like, here's the graph of the function f, and we have that it's defined between these 2 points a and b. So naturally this point is a f of a, and this point is b f of b. And let's say we want to find the distance along this graph from here to here. How would you do that? Well, turns out that it's an integral. The arc length, which for some reason is always denoted s. I don't know why s. I'm sure there's a reason, but I don't know it. This is the integral from a to b of the square root of 1 plus f prime of x squared dx. And often this is written as integral from a to b of the square root of 1 plus dy dx squared dx. Okay, so, and you know, that's just the same thing, right? Because y is f of x. So that's about all that I'm going to be introducing for today. The rest of this lecture is just going to be examples. It's always just find the arc length of this curve from this point to this point, and it's always just going to be put it into this formula. So, find the length of the curve y equals root 2 minus x squared from 0 to 1. By which it means x equals 0 to x equals 1. Alright, so all we have to do here is first we take the derivative. Dy dx is 1/2 2 minus x squared to the negative 1/2 times negative 2x according to the chain rule. This is the same thing as negative x over the square root of 2 minus x squared. And so then you just put that in here. So the arc length from 0 to 1 is the integral from 0 to 1 of the square root of 1 plus this derivative squared, so negative x divided by 2 minus x squared, square root, and square all of that, dx. Well, if you square that, then of course the square root on the bottom cancels out, and the top just becomes x squared. So then this becomes integral from 0 to 1, square root of 1 plus x squared divided by 2 minus x squared dx. You can find a common denominator between these two. You can write 1 as 2 minus x squared over 2 minus x squared. When you do that, you can just add the numerators together so that this becomes integral from 0 to 1 of the square root of 2 over 2 minus x squared. Okay. And so now we just need to figure out what this integral is. Easiest way to do that is to understand that this looks an awful lot like the derivative of the arcsine, because this can be rewritten as the integral from 0 to 1 of 1 over the square root of 1 minus x squared over 2 dx. X squared over 2 can be understood as x over root 2 squared. So this is 1 over the square root of 1 minus x over root 2 squared dx. U equals x over root 2. Du equals 1 over root 2 dx. In that case, this becomes integral of root 2 1 over square root of 1 minus u squared du. And the bounds should change as well. When x is 0, u is 0. When x is 1, u is 1 over root 2. And then this is just square root of 2 times arcsine u, evaluated from 0 up to 1 over root 2. By definition, that just means root 2 arcsine of 1 over root 2 minus root 2 arcsine of 0. Arcsine of 0 is 0. Arcsine of 1 over root 2 is pi over 4. So this becomes pi root 2 over 4, and that is our arc length. Okay? So it's nothing more than just take the function and put it into your formula. But, as I mentioned in the lecture on Taylor series, that's not as easy as it sounds, always. Okay? Also, as you can see, most of the work here was trying to figure out this integral. And so therefore, if you're a bit rusty on chapter 7, then this is a good time to review it. Okay, let's do another example. This one will be y equals, let's see here. Y equals x to the 4th divided by 8 plus 1 over 4x squared. We're going to find the arc length from 1 to 2. Okay, so again, we just take its derivative first. dy dx is going to be, let's see here, 1/2 x to the 3rd minus 1/2 x to the negative third. Right? All right. And then the arc length is going to be the integral from 1 to 2 of the square root of 1 plus the derivative squared. You can distribute that. So this turns into integral from 1 to 2, square root of 1 plus, let's see here, 1/4 x to the 6th minus, oh wait, this should be to the negative 3. That's better. Minus 1/4 minus another 1/4, that makes minus 1/2, plus 1/4 x to the negative 6. One plus negative 1/2 is just positive 1/2, and so then this becomes integral from 1 to 2 of the square root of 1/4 x to the 6th plus 1/2 plus 1/4 x to the negative 6 dx. Okay, so now you just have to do that integral. And you're probably looking at this and saying, like, how would you take the antiderivative of that thing? The truth is, this is easier than it looks. It looks extremely hard, but it's not, because it turns out that this thing under the square root is a perfect square of some other function. Let's take a minute to talk about why that is. So we have 1/4 x to the 6th plus 1/2 plus 1/4 x to the negative 6. If I were to factor out x to the negative 6 here, in fact, let's factor out 1/4 x to the negative 6. This becomes 1/4 x to the negative 6 multiplied by x to the 12th plus 2x to the 6th plus 1. Now this thing can be factored. This thing can be factored because it's a quadratic in terms of x to the 6th. This is x to the 6th squared, this is x to the 6th, and so we can do it. So this becomes 1/4 x to the negative 6 times x to the 6th plus 1 times x to the 6th plus 1, which is just x to the 6th plus 1 squared. And then let me just point out that this is the same thing as x to the 6th plus 1 squared divided by 4x to the 6th. So what we're actually dealing with here is the integral from 1 to 2 of square root of x to the 6th plus 1 squared divided by 4x to the 6th dx. Well, the square and the square root cancel each other. So then this becomes integral from 1 to 2 of x to the 6th plus 1 divided by 2x to the 3rd dx. You divide these two polynomials, and what you get here is, well, first of all, we can take out the 1/2. We have 1/2 integral from 1 to 2, x to the 3rd plus x to the negative 3rd dx. And then that's an antiderivative that you can do, right? That's just the power rule for antiderivatives. So then this becomes 1/2 1/4 x to the 4th minus 1/2 x to the negative 2 evaluated from 1 to 2. This ends up being, let's see here, 1/2 times 1/4 times 2 to the 4th minus 1/2 times 1 over 2 squared minus 1/2 1/4 times 1 to the 4th is just 1 minus 1/2 1 squared is 1, so it's this. And of course this can be simplified, but this is the answer, no matter how we choose to write it. Okay? This is a very common setup when people are making arc length problems. Okay? When instructors are designing arc length problems, it's very common for them to come up with a function so that when you take 1 plus the derivative squared, it turns into a perfect square of some other function, but it definitely doesn't look like it. Okay? And so in those cases, you always have to do this weird factoring. And then turn it into a square, and then that cancels the square root. Okay? So that's very common. You will definitely see that on your homework. Let's see here. Next up, we have natural log of cosine of x from 0 to pi over 3. So find the arc length of y equals cosine x, no, natural log of cosine of x over the interval from 0 to pi over 3. Again, we just need to take the derivative first. So derivative, dy dx, this is going to be 1 over cosine x times negative sine x. This, by the way, happens to be the same thing as negative tangent x. In that case, the arc length is going to be the integral from 0 to pi over 3 of the square root of 1 plus this thing squared, so 1 plus negative tangent x squared dx. Now, of course, negative tangent x squared is just tangent squared x. So this is integral from 0 to pi over 3, square root of 1 plus tangent squared x dx. It so happens that 1 plus tangent squared x is secant squared x. So this is integral from 0 to pi over 3, square root of secant squared x dx. Now, strictly speaking, the square root and the square can't necessarily cancel each other because you'll have to say the absolute value of secant x, but secant x happens to be positive over this interval, so we don't even have to worry about that. So this is just integral from 0 to pi over 3, secant x. Remember that one? Yes, so the very first example I did about trigonometric integrals in 7.3, I think, was this. And the way that you had to integrate this one was you had to multiply top and bottom by secant x plus tangent x. So multiplying by secant x plus tangent x divided by itself, of course, is the same as multiplying by 1, which does nothing. You distribute that through, and then you can do a u substitution on that. In any case, What this eventually turned out to be was the natural log of the absolute value of secant x plus tangent x, evaluated from 0 up to pi over 3. So, natural log of the absolute value of, let's see, secant of pi over 3, that would be 1 over the cosine of pi over 3. Cosine of pi over 3 happens to be 1/2, so secant of pi over 3 is 2. Add to this the tangent of pi over 3. Tangent of pi over 3 would be sine of pi over 3 over cosine of pi over 3, and that just turns out to be square root of 3. Subtract from this natural log of secant of 0 would be 1 over cosine of 0, which is 1. Tangent of 0 is sine of 0 over cosine of 0, which is 0. Natural log of 1 is 0, so this is just natural log of 2 plus root 3. Okay, here's a bit of a weird one. This one says find the length of the curve y equals the square root of x minus x squared plus the arcsine of the square root of x. I bet you're expecting me to say over this interval or that interval, right? Well, I'm not going to. I'm not going to because actually this curve has a finite length because its domain is a finite interval. This thing is only defined on the closed interval from 0 to 1. Which means that if we want to find its length, then we're integrating from 0 to 1. By the way, think about why this is. It's not immediately obvious why the domain is the closed interval from 0 to 1. Anyway, first we take the derivative. So dy dx, this is going to be 1/2 x minus x squared to the negative 1/2 multiplied by 1 minus 2x, by the chain rule, you know. Then we have this one, 1 over the square root of 1 minus the square root of x squared, multiplied by the derivative of the square root of x, which is 1/2 x to the negative 1/2, again, chain rule. This is 1 minus 2x over 2 square root of x minus x squared. This one over here, well, square root of x squared is just x. So this is 1 over 2 square root of x times square root of 1 minus x. You can multiply these two together, the square root of x and the square root of 1 minus x. So then this becomes 1 minus 2x divided by 2 root x minus x squared plus 1 over 2 root x minus x squared. And they happen to have a common denominator, so you can put the numerators together. This becomes 2 minus 2x over 2 root x minus x squared. Then you can cancel a factor of 2 from top and bottom, and this becomes 1 minus x over square root of x minus x squared. Okay, so then the arc length is just going to be same formula as we always use for arc length. Integral from 0 to 1 of square root of 1 plus that thing squared, so 1 minus x over the square root of x minus x squared squared dx. This turns into integral from 0 to 1 of the square root of 1 plus 1 minus x squared divided by x minus x squared dx. X minus x squared can be factored into x times 1 minus x. So then this becomes integral from 0 to 1, square root of 1 plus 1 minus x squared divided by x times 1 minus x dx. Let me just draw a partition here so we don't get confused. 1 minus x cancels. So then this becomes integral from 0 to 1 of the square root of 1 plus 1 minus x divided by x dx. 1 can be written as x over x. Then you add these two together with a common denominator. This becomes integral from 0 to 1, square root of 1 over x. And of course, that's just the same thing as the integral from 0 to 1 of 1 over the square root of x. Now at this point, you should notice something weird. This is an improper integral. It's the function, the integrand, is not defined at 0. And therefore, we're going to have to do it like an improper integral. So, this is the limit as, I'm going to call it a, approaches 0 from the positive side of the integral from a up to 1 of, let's see, 1 over root x can be rewritten as x to the negative 1/2. You do this antiderivative by taking the power rule. So this becomes limit as a approaches 0 from the positive side. 1/2 x to the positive 1/2, evaluated from a up to 1. Then this just becomes limit as a approaches 0 from the positive side, 1/2. 1 to the 1/2 is 1, minus 1/2. A to the 1/2 is just the square root of a. As a approaches 0, this last term approaches 0, and so then this just becomes 1/2. However, oh, I made a mistake. That's not how you take the antiderivative. You have to divide by the new exponent. So actually, this should be like that. Dividing by 1/2 is the same as multiplying by 2. Okay, then this becomes limit as a approaches 0 from the positive side, 2 minus 2 root a, and then that's just 2. That's our answer. Okay. All right, and let's do one more. So this problem I brought up before, and I wasn't sure how to do it at the time, so I have a bit of a score to settle with it. Find the arc length of y equals, what is this, 1 minus e to the negative x? Yeah, 1 minus e to the negative x from 0 to 2. This is weirdly hard. It doesn't look like it should be that hard, right? But it's, yeah, you'll see. Okay. So first thing we got to do, as always, is take the derivative. This becomes e to the negative x. So then the arc length is going to be the integral from 0 to 2 square root of 1 plus e to the negative x squared. So let me actually just write that. E to the negative x squared dx. And then you've got to do that integral. Turns out that integral is not so easy. What you have to do is a u substitution first. You say u equals e to the negative x, then du equals negative e to the negative x. And by the way, that second statement right there can be rewritten as negative 1 over e to the negative x du equals dx. But e to the negative x is just what we call u, so this actually just says negative 1 over u du equals dx. Okay, so now this integral becomes integral from 1 up to e to the negative 2. Okay, we have square root of 1 plus u squared divided by u du, and let's not forget the negative sign. And now this integral looks pretty innocent as well, right? It's not. This one you have to do by a trigonometric substitution. You have to say u equals tangent theta, and then du equals secant squared theta d theta. So then it does the whole trigonometric substitution thing. This ends up becoming, let's see here, integral of negative square root of 1 plus tangent squared theta divided by tangent theta secant squared theta d theta. And let's not even bother with the bounds for right now, because yes, we're doing a substitution. We can change the bounds, but typically when you're doing a trig substitution and you're changing the bounds with that, students tend to find it a little bit confusing. So let's just leave the bounds alone for right now. Right, so anyway, tangent squared plus 1 is secant squared. Square root of secant squared is secant. So then we have secant cubed over tangent. So we have negative integral of secant cubed theta over tangent theta d theta. And then you have to do that antiderivative. This one is most easily done by saying this is negative integral of tangent squared theta plus 1 divided by tangent theta secant theta d theta. Then you can divide both of these terms by tangent theta. What you'll get here is negative integral of, well, okay, tangent squared theta divided by tangent theta is just tangent theta. You multiply by secant theta and then you get secant theta tangent theta. Then 1 over tangent theta times secant theta. That happens to be cosecant theta, which you can determine by just splitting everything into sines and cosines. So we have cosecant theta right here. So then this this becomes negative integral of secant theta tangent theta d theta minus integral of cosecant theta d theta. Okay, negative integral of secant theta tangent theta is just negative secant theta. As for this one is very similar to finding the antiderivative of secant theta. For this one, you have to multiply by cosecant theta plus cotangent theta divided by itself, and then do a u substitution on that. In any case, what you end up with is negative log absolute value cosecant theta plus cotangent theta plus c. And then you have to do that whole right triangle thing because we just did an indefinite integral here. So the details are in my notes. I'm just going to wrap it up just because this is not really the point of this lecture. It ends up being actually, you know what? Even the answer is so complicated that I'm just going to leave it to you to read. It doesn't come out to be a nice number. It's very irrational. So hopefully this last one doesn't intimidate you too much because yes, this one was quite hard, but they're not all this hard, okay? Of course, homework is up. Even during the Thanksgiving break, let me know if you need any help and I will be happy to help you out. Get some practice with that.